When I first got interested in fossils, it was on a trip to upstate New York. I had been invited to dig some of the Devonian fossils, trilobites and gastropods and all different types of creatures from way back hundreds of millions of years ago. Well, after learning about all these different creatures and their lives in deep time, I started to get interested in prehistory. And naturally, the next thing I wanted to know about was what came before that. What did we see in the world before these already very ancient creatures? Well, this began a journey going back way into the Precambrian and Cambrian fossils that can be found in our area. Over the years, I've been lucky enough to see many places and able to even collect in some of them, and I wish to share this with you in this video. So come along with me on this journey, and I will show you what I found along the way. Oh, and if you wish to support me and my channel, if you like these fossil hunting videos, please go ahead and give me a thumbs up, or better yet, even subscribe. This will make fossil collecting videos like this pop up more often in the YouTube feed. Well, let's start our journey. Let's take a look at these Precambrian to the Cambrian fossil. Any story that starts with the Precambrian era is going to have to start by the ocean, because that's where all life was. Life started in the ocean somewhere in the very early Precambrian. What we can glean from the fossil record tells us that it probably started very quickly. Earth and our solar system formed about 4.6 billion years ago. The sun formed from a cloud of gas condensing on itself over its own gravity. Gravity is the strongest force in our universe. Gravity would start pulling all these tiny bits of dust together. The dust would clump together with no other major forces acting on them, pull towards each other, making larger and larger concretions of materials out in space. There'll be dust and metals all starting to stick together, and those not becoming part of our sun would end up in a large rotating disk around it. Within this disk, more collisions would occur, forming small planetesimals. Maybe 100 or so of these small planetesimals would eventually collide into each other and make the planets as we know them today. There was to be one major event on our own planet that would make life possible about to happen within the first 500 million years of our planet's life. The heat of crashing impacts caused our surface to become molten. We don't know how long it took for our Earth's surface to cool down enough to solidify. It probably didn't take very long on a geologic scale. Remember, geologic timescales are used, measured in tens or hundreds of billions of years, but probably not terribly long geologically speaking, our surface cooled. But then, about 4 billion years ago, we were about to have another major impact. A planet about the size of Mars crashed into Earth under the Theia hypothesis. Theia hypothesis is a pretty well-supported idea of how our Earth got a much larger than average core for a planet our size, and the formation of our abnormally large moon. This animation that I made will show the latest thoughts on how this occurred. The size of the cores of these two planetesimals are only approximate because of the limitations of the software that I was using, but it gives the idea of first the planets crashing into each other about 4 billion years ago. It shows the cores of the two planets, these iron cores, merging together in the one larger planet, which would become Earth. Over time, the debris cast out from the collision, which was circling the Earth, was pulled together by gravity, forming our moon. Our moon is mainly rock and has very little iron. Now, as a result, we have this strong and powerful iron core, and it is rotating just like our planet is. The rotation of our iron core acts as a dynamo. Its rotation causes a magnetic field to build up. This magnetic field has been extremely beneficial to us. We would not be here without it because it blocks many forms of radiation, including the solar and cosmic radiation, which we are constantly bombarded by. Without this, the sun would have easily been able to blast away most of our atmosphere, and we would be a planet much like Mars. Very little atmosphere and very little protecting it from the solar radiation. Our planet ended up with a much larger iron core than it otherwise would have had. They had crashed into us. We absorbed the core of that planet. All that iron, molten iron, that is still hot underground today. It drives the plate tectonics that causes changes on our globe, and it also spins relative to the spin of our Earth, causing a magnetic field to develop. This magnetic field is really important. Magnetic fields are very good at blocking radiation, and much of the extreme radiation that comes from our sun is blocked by this magnetic field. Otherwise, life on land would not be possible at all. But if we go back to a simpler time, there was no life on land. The earliest life came from some chemical reactions going on in the ocean. There are different theories about how this came about. Some say it was at the deeper parts of the ocean where there is hydrothermal vents. Others say it was around concentrations of radioactive materials. Something was giving us energy, something caused molecules to not only do chemical reactions, but eventually take on the replicating processes that would lead to life. Once fairly complex molecules are able to replicate, well then Darwin's in the driver's seat. Replication and survival of those patterns that repeat the best will end up driving us towards more and more complex and more successful forms of life. However this started, it was very simple in the beginning. We think very simple molecules, much like RNA, basically just nucleic acids that were able to stick together, made some of the first self-replicating molecules. How did this happen? We think nucleic acids like DNA and RNA first started to stick together and form chains of molecules. They basically will stick together on specific sides, kind of the way Legos. With Legos, they usually have the interlocking pieces that go in one direction or another, but not multi-directional. So these amino acids and nucleic acids, ammonia and methane, all these things in our early ocean would eventually make what they call the primordial soup. All the different ingredients that could potentially lead to life. We started to get chains of nucleic acids starting to stick together. Well, eventually, just by accidents, they probably got the 100 or so in the right order to be able to replicate a ribosome. Once they can make ribosomes, they can make exact copies of themselves. So probably random chance, but they had literally billions of years to just find the right combination, and we end up with these self-replicating RNA or DNA molecules. Where did cell membranes come from? We need those. Well, surprisingly, this stuff naturally forms in the ocean. The cell membranes are really not much more than bubbles, and in fact they're lipid bubbles, and we see them all the time. They actually form naturally in the ocean. If you ever seen that sort of frothy stuff where waves are washing up on the beach, well, those little bubbles are actually lipids. They naturally form. And so we had to have this combination of some nucleic acids getting trapped inside of these lipid bubbles in the ocean with a very most simple self-replicating cell. At least that's where the evidence is pointing to right now. We do know, though, that from fossil evidence, all life started in the ocean. Started with very simple, probably chemotropes, things that make food from chemicals, and eventually, using these newly formed membranes, we're able to develop proteins, also using nucleic acids to replicate them, which would eventually lead to the proteins such as chlorophyll that make photosynthesis possible. So once photosynthesis started happening, it was extremely successful. They could make their own food. They didn't have to randomly absorb the right chemicals or intentionally absorb the right chemicals as they evolved. They were able to make their own food, and the cyanobacteria, this photosynthetic bacteria, became a dominant force of life on our planet for hundreds of millions of years to come. But how do we know this? How do we know that life was doing photosynthesis billions and billions of years ago? Well, it turns out that we have something called stromatolites. Stromatolites are just basically these curved mounds of rock. The oldest found on Earth go back 3.8 billion years. We were able to find some locally in New York that were not quite as old. They were at a place called the Petrified Sea Gardens. We visited the Petrified Sea Gardens in upstate New York a number of years ago. It was being run by Native Americans from the Iroquois. I believe it is still open, and still you can come and take a look at these very ancient stromatolites. What these mounds are made from are basically just excreted materials from cyanobacteria. They are still making these now in a few places on Earth, but they were much more common in the very early Earth. We actually find them going back 3.8 billion years, not very long after the Theia impact. So apparently the crust had solidified enough to give us an ocean formed above it about 3.8 billion years ago, and all the chemistry that had to come together to form life all formed within that first 200 million years or so. We know this though because of these stromatolites dating back 3.8 billion years. Here's one that's on display at the Smithsonian Institution in Washington, D.C. This one is one of the earliest, about 3.7 billion years, and it tells us that life was thriving on this very ancient sea floor. Just very simple bacteria doing something really important. They were doing some of the first photosynthesis. We see stromatolites, which are just mounds of excreted material. Some of the stuff they would take in, they would not use, but excrete out, kind of the way a snail excretes out calcite to build its shell. Well, the bacteria was excreting out these unwanted isotopes and eventually building up these rocky mounds. The rocky mounds still exist. That's one line of evidence that we know there was photosynthetic bacteria. Also, when we check these rocks, we also see the chemical signature of bacteria, basically broken down bacteria and other waste products preserved in the rock, showing us that these photosynthetic bacteria were thriving. This is what the stromatolites look like in a 3D form. The ones we saw at the Petrified Sea Gardens were all cut by glaciers, so you see that curvy pattern, but that curvy pattern is sort of a cross section. This is what they look like three-dimensionally. There's sort of these round tufts. This one's a baby compared to the other ones. This one is only about 400 million years old. Comes from near Schoharie, New York. So these things have been being formed, giving us one of the earliest indications of life on Earth. Here, when I turn this to a section that's kind of broken away, you can actually see the swirling pattern. So this is the pattern of layer after layer of excretions by cyanobacteria, or something very similar to that, doing the first photosynthesis on Earth. It built up. When the organisms lived, they took in seawater, which had a lot of minerals. They excreted out the parts that they didn't need or didn't want, and it ended up leaving this film on the bottom. Well, after many generations of this bacteria, you actually get these visible layers showing up in the rock as this formed over the course of maybe many centuries or many thousands of years. Bacteria growing in the same place, excreting the same materials, and building the structure up towards the sunlit sea. So this was probably it. The only thing living on the bottom of our ocean was very simple bacteria, also something else called archaea, which is very similar, single-celled organisms just like bacteria, living that way for billions of years, just pumping out, just taking in CO2, pumping out oxygen. Well, all this oxygen that they were pumping out caused a reaction in the water. The water used to have a lot of iron and other suspended minerals within it, but the oxygen caused it to rust. The oxygen would bond caused it to become a little bit heavier and sink below the water, making many bands of this rusted iron material. And in fact, we can look at these rocks with the banded iron and actually see when the photosynthesis was flourishing. We had a lot of photosynthesis, a lot of bands of rust. We have less photosynthesis, many bands of the bluer iron. And what was about to change was our entire ocean. If you looked at the Earth from a distance, 3.6 or 3.8 billion years ago, it would have looked red. There was a lot of irons and other materials floating around in the ocean. Most of the nutrients that it has in it now, except it did not have any oxygen. Those cyanobacteria that evolved in excess of 3.8 billion years ago, well, they were starting to release oxygen as a waste product. It was toxic. It was like cyanide to them. It would kill them. They released the oxygen, it went into the ocean, and little particles of iron and other metals started to oxidize or rust. And we started to get these banded iron formations settling on the floor. Blooms of these cyanobacteria releasing oxygen into the water. It released it into the water. Particles in the water like iron started to rust. They bonded, got heavier, sank to the bottom of the ocean. Layer after layer built up. This rock is from Australia, and it has this banded iron. The layers of red are times when the oxidation was high, when there are times when the biological activity was limited. Maybe it was colder seasons, maybe it was changing depths of the ocean, but there were times when they didn't bloom as much, and then you have bands where there was less oxidation. These banded iron formations show up all over the world. Now this one I didn't go to Australia to get. It would be a nice trip, but no. This one actually got at that New York, New Jersey fossil show that comes around once a year. You could actually take a look at the episode where they had a lot of this and a lot of other really great scientific materials. I'll put a link at the end of the video. So over the course of, I don't know, days, weeks, seasons, we have these different layers of the red oxygen-saturated iron falling to the bottom of the sea. This gold stuff is jasper, basically a silicate, when there was less of that activity going on. And it records a record of these cyanobacteria blooms billions of years ago. This told us that lots of oxygen was going into the ocean. Our ocean was changing. It probably turned the bluish color it is now as it lost a lot of the suspended iron particles. So I'm really glad that this chart came out because it helped solve a mystery for me. For years, I was wondering why whenever I dig in early Paleozoic rocks, I tend to find very anoxic, very dark rocks that indicate very low oxygen. When we had this great oxygen event that should have happened about 2.1 billion years ago when all that cyanobacteria was pumping out all this oxygen, why am I finding such low oxygen in the early Paleozoic? And the answer is, as this chart indicates, there's a lot more to the story. It turns out that when the oxygen was pumping out of the cyanobacteria in the ocean, well, it wasn't making it to the atmosphere. I had pictured it just going up in air bubbles and being released, creating our new atmosphere, but there was a lot more to that. What actually happened was the water had many minerals, particularly iron, that were oxygen deprived. They had never reacted with oxygen, so all the oxygen was getting immediately absorbed up before it could go up and fill our atmosphere. It turns out that's not going to be until much later, after all the minerals in our oceans reacted with the oxygen, then it could be released up into the air. And we'd find that even then we didn't get a oxygen-rich atmosphere because there were so many things on the continents to react with the oxygen, sulfur and other minerals. So it wasn't going to be till much later on in Earth's history that we actually get abundant oxygen like we have now. I looked at these dark shales. These dark shales just didn't make sense to me. because we have abundant trilobites, which should indicate lots of life going on. If it was low oxygen, well, then there shouldn't be all this life. If the cyanobacteria had given us so much oxygen, then why was all these lower Paleozoic fossil sites looking like they have such oxygen-poor environments? Well, it turns out there was a lot more to the story. The trilobites we see here, although they're abundant, they're only one species. There's not a lot of variety going on. Apparently, it's a single species that had just adapted very well to the low oxygen environment. You don't see a variety of other creatures here. So it looks like it was actually a low oxygen environment that continued through all the way up until the Devonian era. But I got way ahead of myself talking about the lower Paleozoic when we were way back in the early part of the Cambrian period. We were first seeing the great oxidation event. We were seeing the first oxygen getting released by some of the first photosynthetic microbes into our atmosphere. The whole story of aerobic and anaerobic microbes is a little bit more complicated, but for the purposes of the film, we're going to say that the photosynthetic microbes were making oxygen, which may later lead to aerobic microbes, ones that would be using the oxygen. But for now, let's take a look what's still going on in the ocean. This was it. This was all of life, just this mushy stuff growing on the bottom of the sea, until something happened about 2.5 billion years ago that was about to change everything. We were going to see early cells become infected. They become infected with other smaller microbes. But something really weird happened. When we get infected with something, we usually become sick, whether it's bacteria, viruses, whatever, it usually makes us ill. But imagine if you got infected with something that made you 20 times more powerful than you ever were. Well, this is what happened. We ended up with mitochondria. Mitochondria has its own genome. We believe that it evolved originally as a separate bacteria, but invaded larger cells. And because this mitochondria didn't make these cells sick, it actually gave off ATP, something the cells need. It actually made them more powerful. On average, about 18 times more powerful than they would have been without the mitochondria. This would eventually lead to more advanced cells, cells with organelles, and eventually cells with a nucleus. What we're looking at here is a sample of the gunflint chert. This is a chert, or basically a silicified rock, that caused microorganisms to be preserved within it. It basically got locked in the crystallizing silica and was preserved for billions of years. This rock is about 2.5 billion years old, but what's really remarkable about it is that it has the fossilized remains of microorganisms. And these microorganisms, to the best of my knowledge, are the first known eukaryotic cells. The first cells that have a nucleus that show up in the fossil record back 2.5 billion years ago from the gunflint chert formation. I'm really fortunate to have this. I was able to get this by trading with some people up in Michigan, a Michigan Geological Society. I traded some fossils from New York, New Jersey, and Pennsylvania region for this sample from Michigan. So I'm very glad to have it because this is really important as far as understanding the Precambrian, the first eukaryotic cells that show up in the fossil record, exquisitely preserved inside this chert. So what we are looking at here is a marsh, and we're looking at what is growing here. And I'm not talking about the grass. These grasses are actually very recent geologically. What I'm talking about is what's living in the mud. And what's living in the mud, we're going to see are layers of algae. And you might wonder why I care so much about what's going on with the algae in the mud. Well, for billions and billions of years, this is basically all there was to life. layers upon layers of this greenish blue algae that you see in the mud. Well, these mud mats existed all over the bottom of the ocean. Picture a world where you were stepping in nothing but green mush everywhere you went, everywhere on the beach. Well, that was kind of like the early ocean, covered with nothing but algae, which was probably the most advanced life at the time, and an ecosystem of microbes living on the sea floor. Pretty much microbes everywhere, nothing disturbing them, nothing eating them, nothing disturbing them other than weather and storms, living all over the earth. This would be our ecosystem for perhaps 1 billion years or so. Nothing beyond that going on at the seashore. So here's the next clue in the Precambrian transition in our northeastern rocks. This rock is a felsic metamorphic rock. They can be found all along the west side of the Hudson River, up a little bit north of New York City. Felsic is a geologist term that refers to rocks that are generally very low in metals compared to other rocks, compared to, say, ocean rock, which is very high in metals. These felsic rocks are not only light in color, they're light in weight, and tend to be very low in metals. So what's really interesting to the history of our planet is not the garnets, they are interesting, but it's actually something else that is in this rock. If I turn this over, we can see lots of sparkly little silver-colored items here. And it's not silver, it's actually graphite. And this helps tell the story of the supercontinent Rodinia, which formed in this area. Rodinia was a supercontinent that formed about 1.2 billion years ago. It formed right about where we are in North America. When it formed, a lot of these rocks came up and formed an enormous mountain chain, probably comparable to the Himalayas nowadays. And recent papers suggest that one of the reasons why this mountain chain was able to form and come so high above ground level was because of all the graphite. This felsic rock contains a very high content of graphite compared to normal metamorphic rocks. Well, what does that mean? We believe that the graphite is from carbon that was concentrated from living organisms. These living organisms, when they were living, sequestered a lot of carbon. It ended up on the seafloor and ended up into the probably sedimentary rocks of the time. Well, when the continents came together, these sedimentary rocks were actually much lighter than the ocean floor rock and probably even other continental rock with such a high graphite content. So this may have actually helped the very high rise of the mountain chain that formed the backbone of Rodinia, starting about 1.2 billion years ago. So the graphite concentrations, we believe, are from carbon concentrations from living organisms, Precambrian life that was living near the continental margins at least at that time, sometime before the formation 1.2 billion years ago. So probably evidence of more of these abundant algal and cyanobacterial reefs that were probably thriving when Rodinia formed. In the case of Rodinia, we're going to see life helping to form the world, help building that supercontinent, and the supercontinent being formed by life, this graphite in the rocks, causing it to rise so high and forming these very significant mountain belts across the early supercontinent. Now, at the end of the Neoproterozoic, we get a new oxidation event. The oxygen that had been released by life, by photosynthetic algae and bacteria, had saturated the upper ocean to the point where oxygen was escaping into the atmosphere. It had reacted with all the sulfides that were being released by weathering continents and saturated those metals as well. Now the leftover oxygen had nowhere to go and could enter our atmosphere. We were starting to get a world similar to what we have now. However, all this oxygen was going to lead to another major catastrophic event where we have high CO2, our planet tends to warm. When we have high oxygen, our planet tends to cool. All this abundant oxygen now going into the atmosphere was to have a major cooling event on our planet. So it looks like this vast supercontinent of Rodinia had its start with a lot of the generations of cyanobacteria and algae all absorbing carbon dioxide, giving off oxygen, and sequestering a lot of the carbon, which would eventually become part of the rocks. Well, all this oxygen that these microbes were producing also had another huge effect on planet Earth. We were about to enter the Snowball Earth phase. Not the only one, but a very recent one, geologically, about 700 to 630 million years ago, that may have covered nearly all of Earth with glaciers. The term Snowball Earth refers to the probable appearance of Earth, basically this white glacier-covered ball floating out there in space. A couple of things contributed to this. The low carbon dioxide due to the use by the bacteria and algae, the enormous amount of oxygen which now we're entering our atmosphere. Going back to the diagram of oxygen, we can see that starting 2 billion years ago, we started to get a lot of free oxygen in our oceans about 2 billion years after Earth had formed. But it really had stayed at low levels. Well, now we're getting a lot more oxygen going up, but this oxygen going into our atmosphere cools the atmosphere. Carbon dioxide warms it, oxygen cools it. All this oxygen was to lead to the Great Glaciation, Snowball Earth, our entire Earth covered with ice and glaciers for something in the area of 100 million years. A 100 million year ice age. Whoa, that's cold. But what about animals? How did they survive this? Well, it turns out not only did they survive this, but they thrived. We start to see some of the multicellular animals showing up. Now, they don't show up in our fossil record at first. Our fossil record from 1 billion years ago is very poor. We had breakup of continents, we had glaciation, all things that are very poor for preserving fossils. And we had creatures with no hard parts. Jellyfish do not fossilize well. It's very rare that you find them. But how do we know these creatures were even there in the first place to survive this frozen globe? Well, that goes to their DNA. The DNA clock, based on changes in genetic material, indicates that all the different animals diverged from a common ancestor about 1 to 1.2 billion years ago, just when Rodinia was forming. Through Snowball Earth, they were probably locked up under ice from 700 million years ago to about 620 million years ago. How did it survive living under ice for 80 million years? Well, not only did it survive, it thrived. We start to see some of the large multicellular forms showing up at the very end of the Snowball Earth, what we call the Ediacaran period. We see lots of soft-bodied creatures. Originally, they weren't even recognized. It was a great mystery. Why is it that we have no creatures showing up at all, but then every phyla represented in what they used to call the Cambrian explosion, the point where everything shows up in the fossil record? Well, there are some traces. Sponges leave spicules. Even though the sponges don't usually preserve, they have little hardened parts on the inside. Sponges, we think, are the simplest animal. They have very few specialized cells. After that, we believe things like the jellies, the cnidarians, diverge, and later on we get to the bilateral animals, the whole tree of life. However, there was more to the story as well. The Ediacaran brought forth some really strange animals. Animals that, well, sometimes we even question whether they are animals or a completely different type of life form. In my opinion, they probably deserve their own kingdom, but who am I to say? The Ediacaran includes a range of some very bizarre creatures, some of them that have what's called fractal geometry. We are bilaterals. We have two equal halves. Not all animals are bilaterals. The jellies tend to have radial symmetry. Basically, they're circles. The echinoderms, starfish and things like that, have secondary pentagonal symmetry, five-sided, but actually they're originally bilateral when they're in their youngest forms. But fractal geometry, that is straight. That's what you see in trees, where one branch branches off for another and branches off for another and so forth. These fractal creatures seem to be implanted in the sea floor. They seem to grow in equal fractal points in different directions, and there's no animal like that alive today. It looks like some of the Ediacaran species, kingdoms, phyla, whatever you want to call them, went completely extinct. So look at this. We are looking at Nemiana simplex, which is one of those bizarre Ediacaran fossils, which even the experts are not too sure about. Most places that I've seen describing this are describing it as some type of anemone or possibly even a jelly, something probably living on the sea floor. However, not all interpretations have this as a jellyfish-like creature. Some say more like the closely related anemone, and some are even saying algae. But this is one of those things in the late Precambrian that has scientists puzzled. This one is dated about 620 million years, as you can see from the White Sea Formation, which came out of Ukraine. By the way, Slava Ukraini. It's we've all been watching the terrible things going on with Russia invading Ukraine. We're hoping the best for them. We're going to try and support them any way that we can. And hopefully by the time you're seeing this video, the problem will long have been gone. Hopefully Russia will be out of Ukraine. But anyway, very grateful for the Ukrainian people for making this available. And so we're looking at an early, probably an early animal from that very enigmatic and very hard to interpret late Precambrian, the Ediacaran period, which is at the very end of the Precambrian, where we start to see some of these, what looks to be more advanced life. Here we see something else from the time of the Ediacaran. They look like motorcycle tracks. They are actually the trails of some type of creature that was moving along these algal maps. We're starting to see a little bit of mobility turning up in the end of the Ediacaran. This rock sample is from the same formation as Chickee's Rock. It's not from the same location. It's actually from a tributary river not far away from Chickee's Rock that has the same material inside it. And this one has a really clear example of these perfectly straight burrows. These are late Precambrian or Cambrian boundaries, somewhere along that area. And we see perfectly straight burrows. These are things that were living in the sediment. They are pretty much evenly spaced out. If you look at them from the top, there's a pretty even distribution of the little tubes, the entrances to the tubes. The creature is gone, lost to history. I don't believe there are any hard or fossilized body parts of these animals. They're soft, they're worm-like, and they're not moving. They are living in one place. And we believe that this is before any bilateral animals were moving around. This was something living in its place without the ability, without the brains to move, making its living by filter feeding. Chickee's Rock is in Lancaster, Pennsylvania, right on Route 30. Now, this is not a place where we can collect. It's actually protected, as it should be. But it turns out some of the tributaries near the Susquehanna River cut through the same formation. And it is possible, if you're lucky, to actually find a river rock in one of these tributaries that has a nice piece of this early Cambrian scolitis. So the Cnidarians, they could move around, but they lacked direction. In fact, they lacked brains for that matter. They didn't know what they were doing. They were completely unaware of their surroundings. These worm burrows that we see are actually going in different directions. It looks like they wanted to go somewhere. They wanted to be able to build these burrows. They wanted to be able to find food. This is evidence of the first brains, the first type of central nervous system, probably telling these creatures what to do. The first time some sort of sensory organs might be developing. Now, the jellyfish, if you poke it, it will move in the opposite direction. So it does have some neurons, but it doesn't have a centralized processing center. And that's what's going to start to show up in the bilaterian animals. Evidence of these worms with direction can be found in and around the town of Shattuck Landing. There are outcrops of some of this early Cambrian rock that shows the worm burrows preserved in the now slightly metamorphosed shale. A word of caution though, if you do decide to search the area for a nice sample of this early Cambrian bilateral, make sure the land isn't posted. Make sure you have permission to be on the land, because it can be found around the area, but if you go without permission, you're basically stealing. So make sure you get the okay from a landowner to collect a nice sample of this. But this is a really nice piece of evidence of some of the first bilateral movement, the first worms with brains going somewhere. If you take a look at these tiny little Pachyagnostis, these are tiny little creatures on that trilobite line, and what is really interesting about them is they are partly covered with shells. And around this time, we're starting to see all the different existing phyla. We're seeing the cephalopods, those earliest squid-like creatures from the Cambrian, also developing a cone-like shell. We're seeing gastropods, we're seeing brachiopods, we're seeing all the different phyla starting to become shelled at the same time. This was the reason for that term Cambrian explosion, because they didn't understand why everything was showing up at the fossil record already diverse at about 540 million years. Well, the reason was something changed. The phylas were already existing now because we are finding earlier trace fossils of them, but they started to grow shells. All of them did. Well, why does a knight put on a suit of armor? To protect itself, right? We're looking at animals that need to protect themselves. This is probably the first major predation event. This is when creatures are intentionally attacking other creatures or algae to consume and to get their nutrition from. So we're looking at the beginning of an arms race. These two little plates that you see on the agnosta are eventually going to cover the entire creature. Its descendants would become other forms of trilobites and insects and other relatives that eventually protect themselves, as well as all the other phyla starting to find some sort of protection from this new predation. Once again, its evolution is in the driver's seat. They're not deciding to put on armor. What's happening is the ones that are more predisposed to growing this type of protection or stronger outer coverings eventually will thrive, which is the reason why gastropod shells are very different from the type of shells that make up insects. Different animals use different minerals not because they thought it out, but because some were just easier for them to produce. What we're looking at over here is a rock from the Kinzer Formation in Pennsylvania. And this was on a trip to actually go look for early Cambrian fossils. And if you look over here, they actually have some of what they call the small shellies, the small shelly animals, in this case a cephalopod. The cephalopod was probably one of the first animals to actually be able to move up and down in the water column. It secreted a shell around it, and the shell was able to store gases within it. So the animal would siphon gases from within the water. It would store them in its shell and use it for buoyancy to move up and down the water column. So here we have the little cephalopod, more than 500 million years old. And there's other little creatures in here as well. So this tiny little cephalopod was going to have a big future ahead of it. It was probably one of the first things that was able to swim in the water column itself. Most things were either living on the bottom or growing close to the surface, but this was able to use its shell to actually provide buoyancy. It was able to move up and down the water column, and this would give it a huge advantage. These cephalopods could move up and down by adjusting the gases in their shells. The gases were just released by their bodies into the shells. They could actually eject out this gas really quickly and use that to quickly jet itself away from a possible predator or some other threat. So these were able to actually move around quite a bit within the water column. Probably one of the first creatures on Earth that was able to do this. So these little squid, you can see sort of these rusty little stains on this lightly metamorphosed shale. Well, these little stains here in these cone shapes, these are the remains of some of those early little cephalopods. These cephalopods are part of the Kinzer Formation. I found these in Pennsylvania. This might not look like much, but this is something that I'm very excited about. It's something called a phylocarid Brachiocaris. And what this is a little shrimp from the lower to mid Cambrian. I found it in a quarry in Lancaster, Pennsylvania. And when I found it, I showed it to a paleontologist with us who is from Franklin and Marshall College. And when I showed it to him, he had told me that this was the first and only one that had been found in this particular formation. So quite an interesting find. And as far as I know, it's still the only one. Brachiocaris is a shrimp-like creature from the Cambrian, probably a throwback to simpler times. It's showing up as many shrimp-like creatures do, like the enigmatic Anomalocaris does in the Middle Cambrian, in many different forms. What we're seeing is the beginnings of an arms race. This now finally brings us to the Cambrian explosion, the point where all the different phyla start to show up in the fossil record. And our really good example of what was going on is from the famous Burgess Shales from Yoho Park in Canada. The Burgess Shale is a site with very small site actually in comparison to the park, where there's exceptionally well-preserved creatures from the Middle Cambrian. What's special about these fossils is not just that they are Cambrian creatures, but the exceptional soft body preservation. Usually soft body parts don't preserve. These ones seem to have gotten buried very quickly in one event and somehow were protected, buried too deep for microbes to break them down quickly, and you actually get some of the soft parts. These Burgess Shale fossils are not mine. These are from an academic collection that I had been given the chance to look at one time, and brought my camera and took some pictures of these really amazing creatures. You may recognize now what these two prong-looking things sticking out on this rock. These are the front portions of the enigmatic Anomalocaris, the 3-foot or meter-long shrimp that was probably the top predator of its day, running around and eating all the little trilobites. And we see in the Burgess Shale a lot of things that are missing from the fossil record because of this soft preservation, like this morella, this thing that looks kind of like a trilobite without a shell, and that might be exactly what it is. Many paleontologists do interpret it as a ancestor or ancestral cousin to the trilobites, which were also existing at the time of the Burgess Shale. And this really brings us full circle in our Precambrian to Cambrian journey, how we can find fossils from our northeastern region that pretty much show us all the major events of our early history. Thank you for watching. And so, my friends, if you made it this far, thank you so much for watching my film. I hope you enjoyed this fossil hunter's perspective on the transition from the Precambrian to Cambrian world based on its fossils. And let me know what your thoughts are on this. If you like it, go ahead and leave a comment, give me a thumbs up if it was good, and subscribe. Thank you again. Happy collecting.